This is going to be tracking huge files with Git LFS. If anyone's in the wrong place, you should stay here anyway. This is an awesome piece of technology. So like many great stories, ours begins in Paris. It was the 8th of April 2015, and a collection of engineers were gathered from around the world at the annual Git Contributors Summit. And it was being held in Paris this year, the day before GitHub's annual Git Merge conference. Now, the conversation got kind of interesting at this summit, because there are a couple of Atlassian developers who work on Bitbucket conversing with a couple of GitHub engineers who work on GitHub. And traditionally, we're fairly staunch competitors in that space. And Nick Palucci and Rick Olson, who was the GitHubber who Nick was talking to, had a chat like this. Nick said, "Hey, I work for Atlassian on Bitbucket, and we've been building this really interesting new project to solve the problem that Git has with storing large binary content. So we built this new extension to Git built in Go, and we're planning on announcing it at our track session at Git Merge tomorrow." And Rick from GitHub said, it's kind of funny actually, because we've also been working on this new extension to Git. We've built a new tool that solves this problem that Git has with storing large binary content. And we've built this as an extension to Git in Go, and we're planning on announcing it at our track session at Git Merge tomorrow, directly after yours. And Nick went, "What?" That's a picture of James Watt, by the way. And Rick went, "Totes." It's kind of crazy. "What do you call this extension of yours?" And Nick said, "Well, we call ours Git Lob, in terms of long objects like you might find in a database." And Rick said, "Okay, that's really weird because we called ours a 3-letter acronym as well, Git LFS, which stands for Large File Storage." So after some back and forth between the two companies, Nick and Rick and the rest of Atlassian and GitHub decided that Atlassian would open source and mothball the Git Lob project and start porting some of those features over to the Git LFS project instead. Now, fortunately, this was pretty easy because they were both designed in a very similar way. They're both using the same extension points that Git has, and they were both built in the same language. So now we have two competitors working on the same open source project. And this is really good news for the Git community, because it means rather than being fragmented and having non-portable data stored in a proprietary system, you have one solution for solving the problem that Git has with large binaries. So that's why I'm here to talk about tracking huge files with Git LFS. So I'm Tim. I'm a developer at Atlassian. I've been there for almost 10 years working on the Jira and Bitbucket projects. And I'm really excited about Git LFS because I've done a lot of Git evangelism over the years. And every time I give a talk about Git, there's always a few sad faces in the audience. When I talk to them afterwards, it turns out that they're trying to track large binary content. So these are people like game developers who have assets like textures and large models and audio files. These are researchers who have massive result sets that they need to store alongside the scripts that they're using to generate and model these things. These are web developers who have rich media content that they want to store as part of their websites in version control. And these are people like QA engineers who want to take snapshots of databases and store them alongside their func tests in a Git repo. All of these people are traditionally stuck on centralized version control systems or having to cobble together some other dependency management system that allows you to store these artifacts outside of VCS, which is not the most convenient way to do it. Unfortunately, Git LFS is a solution to this problem. First of all, I'm going to step back and take a little look at the Git data model and show you why it has such a hard problem storing large binary files in the first place. Then I'll talk to you a little bit about how Git LFS solves this problem and the different extension points that it uses from native Git to achieve this. Then we'll talk a little bit about how you can convert your existing repositories that may already contain some binary content over to use the Git LFS standard. And then finally, I'll give you some tips for using Git and Git LFS in a team context. So as I mentioned, you need to know a little bit about how Git works under the hood to understand the problem with binary files. Now, when you think about revisions to your code base over time, you're probably thinking of commits, or changes to your code base. Now, in Git, these commits aren't just floating in space. They're related to each other through ancestry. Specifically, each commit has a reference to its immediate parent or parents. You can link up your entire Git history using these references by traversing this graph. And that's what this is actually called. It's a directed acyclic graph, often known or referred to as the Git DAG. It's directed because each node has references to other nodes in the graph, and it's acyclic, and those nodes are actually unidirectional, sorry, those graph edges are unidirectional, which is why it's called directed. And it's acyclic because you never create a cycle. each new object inside your Git data model refers only to objects that pre-existed in it. You can never go back and update those objects. They're effectively immutable. Now, if we put in branches or tags, otherwise known as refs in Git parlance, you have something that gets close to the full schema of what the Git data model looks like. But to understand why Git has such a hard time with binary content, we need to look a little bit more closely at the structure of these individual commit objects. Now, Git has a command called cat_file, which you can pass the -p for pretty flag to, and you can pass it a git commit ID. Now, a git commit ID is actually a SHA-1 hash of that commit object's contents. This is why Git is known as a content addressable file system. Now, this is one of those things that looks really scary when you first adopt Git, because instead of having nice, monotonically incrementing subversion revision identifiers, you have this crazy 40-byte SHA or hash or hexadecimal hash, which you have to copy and write around because you can't remember these things. But the fact that it's content addressable has some really interesting properties. One of the most interesting properties is the fact that it's very easy for Git to detect duplicate objects, which means it's very efficient at reusing things. We'll find out why that's important in just a second. Now, if you run git cat_file and pass it one of these SHA-1 hashes, you can see the actual contents of your commit objects. And they're pretty simple. As you can see, you have a reference to the parent, as we saw before, or parents, so you'll just have multiple parents there if it's a merge commit. You have a reference to a tree object, which is another type of object inside the Git database. Basically, a tree represents a directory inside your Git repository, and the tree referred to by the commit is the root directory. So everything else, all of the contents of your Git repo at that point in time is referred to by that tree. And then you have some commit metadata. So the committer, the author, these are usually the same person depending on what kind of workflow you're using, and a commit message. But other than that, it's pretty simple. Now, if we traverse down and use that cat_file command again to inspect one of these tree objects, you can see that it looks a lot like a directory might look on a file system. You've got the file mode of each of the files at the root level of your repository, and then you have blobs and trees. Blobs are the actual file contents that are being tracked by Git, and trees are the subdirectories that sit in the root level of your repository. Now, we can continue to recurse down through our tree until eventually we get one of these objects for every single directory and file in our Git repository. And if we whack back in a ref, like for example our master branch, we have a more complete view of what the Git data model actually looks like. Pretty simple. And I think one of the keys to learning how Git really works and becoming proficient with it is just understanding how this graph works. Then you can start thinking about merges and rebases and stashes and everything else as transforms on this graph, manipulating these objects and commits. Feel free to take pictures and things, but I'll share these slides on Twitter afterwards as well. So the reason why Git has such a hard time with binary content is because it ends up creating a new one of these trees every time you create a commit. Now, Git, as I mentioned, is very good at reusing objects that don't actually change. But every time you change a blob, you end up or a file in your repository, you end up creating a new blob for it, and that gets stored in your Git objects directory. Now, Git does eventually do some delta encoding of this when it creates these pack files on disk, which are like compressed versions of your repo history. Notably, it does this when it sends it over the wire, so when you do a push or a pull. But unfortunately, depending on the type of content you have in those, that delta encoding and zlib compression may not work very well. So if you're using a raw binary file content type or something like that, or an archive format, then that's not going to compress particularly well when these blobs are created. And that's the problem that Git has with binary files. Let's consider a trivial case where we just have a tree sitting under a commit. So it's just a directory with one file in it, and that file is a high-resolution photo of an elephant in some sort of raw image format where every pixel is encoded as a few bytes with no compression. Now, if we go and change the hue of that elephant to pink, as soon as we create a new commit and add that to our repository, the size of our repository is going to double because we have two blobs sitting in our repo representing that. And it's not going to compress very well. And every time we go and make changes to this, unless it compresses, we're going to end up bloating the size of our repository. Now, this same thing is going to happen with any sort of version control system. Even a centralized version control system, no matter what delta encoding it does, there is just some file types that don't delta encode very well. But with Subversion, all of this bloat happens on the server. And when you clone a Subversion repository, really you're just getting the latest commit that you want to work with. But with Git, it's a distributed version control system. The whole philosophy and a lot of benefits that you derive from Git, all of that awesome performance and those distributed features, mean that you're copying around your entire repository history when you want to work with it. So that means that when I push all of those different versions of that elephant photo to the server, the rest of my team have to pay that tax and pull them down locally, as do my continuous deployment scripts and my CI builds and anything else that wants to work with my source code. So over time, the size of my repository balloons, and all of these pushes and fetches slow down the server and cause additional load. And eventually it just comes to a grinding halt, which is why developers try as hard as possible to avoid checking in copious amounts of binary data into their repositories. So Git LFS is a joint project between Atlassian and GitHub to solve this problem. In a nutshell, the way that Git LFS works is that rather than storing this large binary content directly inside your repository, you store tiny little pointer files that refer to that content. And the actual large file content sits in a separate storage outside of your Git objects directory and outside of your repository. So when you run a Git push on a Git LFS enabled repository, your large files get transferred to this LFS store, and your pointer files, along with the rest of the Git DAG, get transferred to your your LFS-aware Git host, like Bitbucket, for example, as normal. Then when the rest of your team does a pull or a fetch or a clone, the Git DAG gets transferred back as normal, just with those pointer files that weigh in as a few bytes. And then only the versions of those large files that you're actually likely to want to work with are transferred to your local disk. And usually this is just those large objects that are referred to by the tip commit of the branch that you just fetched or checked out. So if we whip out our git cat file command again, and use that pretty flag and pass it one of the SHA-1 addresses of these pointer files, which again are just blobs sitting inside our repository, then there's nothing special about the actual object format, you can see the content of one of them, and they really are super simple. There's a version schema URL, which is basically just a version number for the pointer format. There's only one of those at this point. Then we have an object ID, which is a SHA-256 hash of that object's contents. So unlike Git, which uses SHA-1, Git LFS uses SHA-256. So it's still Git-like, but it's a newer standard. Now there's a couple of reasons for this. The first is that Git is now 11 years old. When SHA-1 was first selected, it was thought to be pretty much perfect. Unfortunately, the SHA-1 spec has been shown to have some theoretical weaknesses, or it's theoretically slightly weaker than its original design constraints. So SHA-256 is basically just a more modern standard that is more secure, at least as far as we know at this point in time. The other reason we use SHA-256 is that some media stores, for example S3, have automatic validation using SHA-256 hashes. So if you use S3 as an LFS store, it's actually very, very easy to reuse something like S3 to do that storage. And then finally, we have the size of the object, which is just its bytes on disk. Now, one of the nice things about Git LFS, as opposed to some other attempts at solving the large media problem that Git has, is that it tries to be as transparent to your regular Git workflows as possible. And it strives to be extremely easy to set up. Now, as I mentioned, it's written in Go, so there's binaries available for basically every platform that Git is available on. And installing it is as simple as installing using your favorite package manager. And then you just run the git LFS install command to get it initialized. Now, all that does under the hood is add a new filter entry to your global Git configuration file. What it does is it binds these things called clean and smudge filters to the LFS filter keyword. Now that LFS filter can then be bound to certain file patterns sitting inside your repository by using the git LFS track command. So what this command does is it adds a new git attributes file to the root of your Git repository, or reuses your existing one if you have that, and then it binds that LFS filter to it. So what this is doing is it's telling Git to, instead of just add or check out these LFS tracked files matching this pattern, instead they should hand them off to this smudge or clean filter. I'll show you how they work just now, in fact. So a clean filter is basically Git's way of saying, hey, I need to do some processing on this file before I write it out to disk when I check it out from a, I need to do some processing on this file before it gets added to my Git repository. So this is when a developer has made some changes to a large file and they want to add it to their repository before they create a commit. Now, instead of just writing it directly to the Git objects directory, instead it gets handed off to this Git clean filter, or Git LFS clean filter. Now, what it does is it takes a SHA-256 hash of that object's contents and then writes it out to one of those pointer files. And then it writes out, but before writing out to the pointer file, it writes that object's content out into a special object cache that sits under your .git repo directory, which is where all the rest of your repository data is sitting, under the LFS subdirectory. So Git itself doesn't know anything about this object's contents. It's purely just a directory for Git LFS to store some stuff in. Then it uses that same SHA-256 hash and writes that out to one of those pointer files that we just saw. And then that's what gets added to your Git objects directory. So instead of adding, megabytes or gigabytes or however big that large file is into your Git objects directory and passing that onto the server, you're only adding a few bytes. Now the opposite happens when a developer runs the git checkout command. If you run git checkout, and basically that means that for every single file that's being checked out, it tries to write that out to disk. But if it comes across one that has a mapping in that git attributes file, then instead of just writing that out to disk straight away, it passes it off to that git LFS smudge command. And it reads that SHA-256 hash from the object ID field, and then goes off and looks in that local object cache to see if it can find one that matches that object's contents. If it doesn't find it there, then it actually reads through to the backing LFS store using a mechanism that I'll talk about in a second. And eventually, once it resolves it, it writes that out to disk instead. So the developer just sees that sitting in their work tree instead of the pointer file. In fact, all of this stuff about pointer files is kind of interesting, but it's pretty academic from the case of actually using Git LFS. Because as a developer, you never actually see these things. You just work with your large file sitting on disk, you add it to your directory, it gets handed off to one of these filters, and then rewritten automatically. And similarly, when you do a checkout, you only see the actual large file sitting on disk. So it's purely transparent to your existing Git workflow. So that's how working with a local repo works. Now I want to talk a little bit about how you actually transfer these files to and from your Git host. So has anyone here played around with Git hooks before? No? A little bit? Cool. So Git has this pretty sophisticated extension system called hooks. If you look inside any Git repository under the .git directory where all of your repo data sits, there'll be a hooks directory automatically created by Git itself. And it has a whole bunch of these sample scripts which aren't enabled by default, but they do some really cool things. You can do things like intercept the commit message generation when you start to do a commit. So that means you can seed commit messages or pre-format them. I used to be a Jira developer, so I'm still a heavy Jira user. One of the things I do is we name at Atlassian our branches after issue keys. So I've got a commit message script that generates the commit message based off the issue key. So it actually inserts it there so I don't have to remember and go back and copy things around. You can also do things like create pre-commit hooks that run unit tests before you can create a commit, which means you've got this really nice property that every commit in your repository automatically passes the tests as kind of like a pre-test before you push to CI. And the one that Git LFS uses is this thing called a pre-push hook. Now, a pre-push hook predictably intercepts the push command and acts immediately before it. So once you've got Git LFS set up and you've added some new files or committed some new large files which have been transformed into pointers, when you run a git push command, you'll see some output from Git LFS saying that it's transferring these files to the server. Now, one of the really nice things about Git LFS is you don't see any authentication prompt here. The way that Git LFS works is it actually piggybacks off your existing authentication with your Git LFS server, regardless of what your LFS store is. And the way they've done that is a really cool piece of architecture that I'll show you in just a second. Similarly, when you run git pull, you'll see some output saying that it's downloading large files from the server if that commit has some LFS files in it that aren't sitting in your local cache. This output is actually coming from that smudge filter that we saw when it reads through to your backend LFS store. And again, one of the really nice things about LFS is it doesn't just work with HTTP repos, which is a big limitation of some of the existing solutions for large files. It also works transparently with SSH. Now I want to talk a little bit about how that works, because it's actually a pretty cool use of hypermedia. One of the interesting things about LFS is that the API that it uses is actually HTTP only, but it also works with SSH. And it also works not only when your LFS store is embedded directly inside your Git host, as is the case with Bitbucket Server, But it can also operate when it's actually an external storage like S3, or you could use something like Artifactory to store your LFS files. And it can even work when your Git host and your LFS store are completely divorced from each other and can have no contact. And the way it does that is by using the client as a proxy to describe exactly which LFS files have been stored in your storage to your LFS-aware Git server. So let's take a little look at how it works in the simple case where you have an HTTP-backed Git repo. Now, when you do a clone, the initial clone goes through as normal. The client says, hey, I want to clone this repository. The server says, hey, okay, here's some repo pack files, which are just, as I mentioned before, a compressed form of that Git objects directory, and they get sent down to the client. Then that smudge filter kicks in. Now, one of the nice things about the smudge filter is you don't have to go and bootstrap that Git LFS repository, because once you've got Git LFS installed globally, that smudge filter gets set up. So when your new repository gets created on disk, Git will know that these files have been bound to LFS and start checking them out and start downloading them from the backing store automatically. So that smudge filter triggers a new request to the LFS-aware Git server, and then it tells the client where that object can be downloaded from. And then the client goes off and downloads that object. And does this once for every large file that needs to be downloaded. Now, the way that this works is that the client simply appends a special path onto the end of your HTTP repo address. And this is the location of the LFS batch API. What it does is it posts up a JSON structure containing the object SHA-256 IDs that it needs to download in order to fulfill this checkout file that it's checking out locally. Then the server responds with a very similar looking JSON structure, but it also has this actions property describing where you can find these objects. Now, this is a pretty cool use of hypermedia, but as I mentioned before, the client doesn't necessarily know how to authenticate with that backing LFS store. So the server also provides a set of headers that the client needs to apply to that download request in order to make it successful. So in the case of Bitbucket's server, because that LFS store is embedded inside Bitbucket as well, we just use a simple signed JWT token, which will identify that LFS client as the principal. And then that is how we authenticate. But this is flexible enough to use with basically any storage medium that has a REST API, because you're basically telling the client how to authenticate with that. So that authorization header could be a bearer token, or it could be basic authentication, or it could be anything that you can dream up, any auth scheme that you want to support. Now, I have a fairly similar way of transferring data to the server when you do a push. The developer initiates a push. In this case, it's a pre-push hook. So before those pack files are transferred, it goes off and tells the server, hey, I have these new objects that I need to upload to your Git LFS storage medium. And then the server tells the client where that storage exists and how to authenticate with it. And then there's also an additional step here where the Git LFS-aware server can tell the client that you need to come back and verify with me once you've uploaded that. Now, the reason for this is to cater for the case where the LFS-aware Git server doesn't have direct contact with the LFS store. So it can't go off and verify that those objects have uploaded successfully. So it's kind of using the client as a proxy to verify that that has actually occurred. So the JSON structure looks very similar. Instead of a download action, you have an upload action. And then you also have this additional verify action, which is completely optional. And with Bitbucket server, because it's actually embedded, we don't bother with that because the server itself can ratify whether it exists or not. Now, that's how it works with HTTP for clones and pushes. But I mentioned that this also works with SSH. Now, SSH is a little bit more complicated because an SSH URL doesn't necessarily map onto a known HTTP URL. So that means that the client doesn't know where to hit this HTTP batch LFS API. So what they've done is added an additional step where there's a special SSH command that the Git LFS aware server has to implement, which will tell the client where that API is. So the way that this works is another clever application of hypermedia. Basically, there's a special SSH command called Git LFS authenticate. It has two arguments, the path to the repository and the operation which you're trying to perform, either a download or an upload, depending on whether it's a clone or a push. And then it returns with its own hypermedia saying, hey, this is the location of the LFS API, and here's how you can authenticate with it. So that's how the auth process works. And I think it's a pretty elegant piece of architecture. But there is something a bit weird about the story that I've just told you, and that is this. I mentioned it's a batch API. But the way that smudge filters work in Git at the moment is that they get invoked once for every single file that gets checked out on disk. So that means that if I've got a computer game with 10 different textures in it, all tracked in LFS, my smudge filter is going to get invoked 10 times. And we're going to do this dance where we hit that hypermeter API 10 times. And that JSON structure, although it is like an array of object IDs, is only going to contain a single one each time. And this is super inefficient because it means that we have all of this back and forth just to find out the location of each of these object IDs. So as of the release of Git LFS 1.2, there's now a special command called Git LFS clone that you can run that obviates this inefficiency. And what this does is it actually disables the smudge filter, checks out all of those pointer files on disk, then batches up all of those object IDs and makes a single request to that batch API. And then it returns those URLs and headers for all of the different locations of these objects, and then it goes through and fires them off. So this is heaps more efficient. Particularly if you're running on Windows, where the overhead of spawning a process is a little bit more, or particularly if you've got high latency between yourself and your Git LFS aware server, because you won't have so many back and forth requests. So that's a little bit about how Git LFS extends native Git. Now I want to talk a little bit about how you can convert your existing repositories over to use LFS. Now, I must admit I did mislead you a little bit earlier in the presentation when I mentioned that Git LFS track command. Git LFS track is awesome when you're creating a new repository that doesn't have any history. But if you run Git LFS track on an existing repo that already has these large binaries, it's not really going to help in terms of reducing your repository size. Because all it's doing is replacing that large content with a pointer file in the new commit. But you still have this deep history with all of these binary files that are taking up heaps of space. Now, seasoned Git veterans who've maybe done some history rewriting may reach for the Git filter branch command and think about going back and rewriting all of those large objects out of history. Has anyone used Git filter branch before? Hey, there we go, cool. So Git filter branch is kind of the, say, Swiss Army knife of history rewriting. As you can see, it's a little bit arcane. What this command is actually doing is going back and deleting every blob that it finds that matches the path big_video.mp4. Now this would work, but it's not a great idea because it means that those files are actually obliterated from your Git history. And you probably added them to version control for a reason. Excuse me. So instead of doing this, you can use this genius/slightly insane command, which will actually go back and rewrite each of those big files matching a particular pattern into an LFS pointer file instead. So you'll still have that history. However, I wouldn't recommend doing this either. Because it turns out, although this will work, this is actually built by Andy Neff, one of the core Git LFS contributors. But there is actually a much easier way to do it these days. There's an awesome tool called the BFG repo cleaner. Does anyone use the BFG? The tool? Yeah, fantastic. Both filter branch and the BFG, there we go. Now, the BFG repo cleaner was originally built to kill the history of a Git repository. So you can use it to remove individual files or remove entire directories, or you can even remove text within files. So like if someone's committed some credentials, or like an AWS key or something like that to a properties file, you can use this to go back and replace that with asterisks, or just remove it completely. Roberto Tiley is a developer who works for The Guardian, and I think that he had some sensitive history or something like that he needed to clean up. And he started messing around with filter branch and then decided that he'd rebuild a new tool based on top of JGit. And one of his initial design considerations was that he wanted to be significantly faster. Now, one of the problems with Git is that it doesn't really have a persistent process. If you look at what happens when you actually run a Git command, you'll see there's a whole bunch of different shell invocations and invocations of these binary files. It's kind of an unholy mess of, well, not mess, it's actually quite nicely designed, but it's a whole bunch of shell scripts and C files. Now, the BFG repo cleaner is built on top of JGit, which is a complete re-implementation of Git in Java. So it does have a persistent process. One of the nice things that it does is as it's going through processing all of these blobs and trees, is it memoizes which ones it's already processed and skips those in the future. Filter branch typically doesn't do that, or in fact, it doesn't do that. So it typically walks the entire DAG when it goes back and processes, which means it can be extremely slow. Which is why the BFG repo cleaner is 10 to 720 times faster. I get that number from, there's a spreadsheet on the BFG repo cleaner homepage, which has the different performance times for running BFG commands versus filter branch commands and a wide variety of open source projects. So it's pretty impressive performance improvement. And the reason why I'm talking about it is because as of version 1.12.5, it has native support for Git LFS. So instead of this brilliant but slightly insane filter branch command, you can simply run brew install BFG or whatever your package manager is. It's written in Java, so it's basically available on any platform that Git is. And then you can use the handy convert to Git LFS flag to transform a pattern throughout your history to LFS pointers instead. Now there is still a little bit of arcanery. You should also use the nob blob protection flag. What that means is it will also rewrite the tip commit of the branch that you're currently on. By default, the BFG repo cleaner assumes that your current commit is in a good state, which is kind of fair when you're trying to delete history. But when you're trying to rewrite history for LFS, it makes sense to rewrite that one as well. So that's how you can rewrite your history using LFS. But if you're working on a project that has a very deep history, or is maintained by a whole bunch of different developers, or is a huge monorepo, then sometimes identifying the large files that you want to track using LFS can be a problem. Fortunately, however, I saw this awesome talk at Git Merge this year from a developer named Charles Bailey, who works for Bloomberg. And he's just open sourced a set of scripts called Repo Factor, which is designed to help you pare down the size of your repository, either by deleting content from it wholesale or by converting it to Git LFS. Now, it doesn't actually do the conversion for you, but it does provide a lot of insight into where this size of repository is coming from. Now, it is a fairly low-level set of scripts. So one of the ways that I've found really useful to use it is by running the generate larger than command, and then you pass it an integer which specifies the threshold in bytes of which blobs you're interested in your repository. And it gives you some kind of arcane output. These are the SHA-1 hashes of each of those blobs, followed by the size on disk of that blob. And then it has this interesting value, which is the average blob size. What this is it goes off and looks at not just each blob inside your Git object store, but it generates a chain of blobs which represent that file sitting at that path over time. So what this is the size of that file averaged out over every single commit in which it was modified. So if that size is high, then that means that it probably doesn't compress very well, and it's a really good candidate for tracking in LFS. So once you've run the generate larger than command, if you pipe that to add file info, then it'll actually run each of those blob contents through the bash file command, which does some content sniffing for you. And now we can see that these are PNGs of kind of a reasonable resolution size. Then if we pipe that to sort, we can start sorting it by that average blob size. And then if we write that out into a text file, and then hand that off to the report on large objects command, unfortunately, you can't just pipe that directly for some reason at the moment. I have to open a pull request for that. Then it'll actually give you the paths for each of those blobs. Now, this is really handy because now we have a ranked list of files in our repository that are massive and causing to bloat out the size of our repo. So we can use that as input to that BFG convert to Git LFS command and start reducing the size of our repository dramatically. Now, once you've done that, all you need to do is enable LFS on whatever Git hosting provider you're using, provided it supports LFS. In Bitbucket Server, literally, you just need to check a checkbox, hit the save button. And we also have automatic support to reading through to that underlying Git LFS store. So all of the rest of the features, for example, our image diffs and things, will retrieve that content automatically. So again, it's transparent to your existing workflow. So now I want to talk a little bit about how you can use Git LFS in a team context. I've mainly been talking about how an individual developer could interact with and rewrite their Git history. But there are some really interesting ramifications of tracking large binary content, whether just directly in Git or Git LFS when you're working with a team. Now, one of the first ones is it can be a big gotcha, and this hurts a lot of people when they first start out. Unfortunately, Git, while it is awesome and easily the best version control system in terms of its support for resolving conflicts, it has no way of resolving the conflicts in a binary file. So you sometimes run into this horrible situation where you've spent all day modifying some large binary on your own branch, only to find out that some other developer has made some similar changes, or maybe some completely different changes, and you have no way to resolve those conflicts. Depending on your binary, the binary format and the nature of the changes you're making, there can sometimes be literally no way to do it other than to just go back and reapply your changes on top of whatever version they've made, or go off and make them do the same thing. So until we get Git locking into LFS, and funnily enough, there was a pull request merged this morning from a Google Summer of Code student who got a proposal off the ground to add locking to LFS. I haven't had a chance to look at the PI yet, but potentially this could be something that's coming out in Git LFS 1.3, but we'll have to see. So until then, just make sure that you notify anyone else on your team who's likely to be modifying one of these large binary files. But we'll be getting locking in there soon. Now, I mentioned that one of the kind of core tenets and points of Git LFS is that you don't have to download every single version of every large binary file. But in some cases, you might actually want to retrieve large binary content that the rest of your team is working on. So the Git LFS fetch command, if you invoke it directly, all it does is go off and download large contents for your current commit. And this usually happens automatically via the Git smudge filter. But you can pass this -- recent flag to it, and it'll actually go off and download large binary content associated with recently updated branches that you have tracking locally. Now, what it means by recent is any branch that has a commit on it that is newer than 7 days old. So this can be kind of handy if you're about to go offline for a while. Maybe you're jumping on a plane and you want to catch up on local code reviews of what other developers have been doing. So if you run this, you'll get all of those large files so you can actually see what the rest of your team have been doing. If you like this behavior, you can actually enable it permanently using the LFS config flag fetch recent always. Now there's also some other ways you can tweak this behavior. You can change that sliding window of what Git LFS considers recent by setting the fetch recent refs days command, config option. You can also set the fetch recent commits days option. And what this means is that instead of just resolving the LFS content for those tip commits of the branches, it'll actually walk back and retrieve it for every commit that's an ancestor of that one back to this day threshold. Now this could potentially be extremely noisy and also involve an extreme amount of data transfer from the server, which is why it's set as a default to 0. But if you work in a smallish team, or if you really need to grab all of that, or maybe you're considering doing some history rewriting or cherry picking or rebasing, and you're not going to have an internet connection, perhaps that would be useful for you. There is also this last config option, fetch recent remote refs. And this one is kind of dangerous because what it means is that it's actually going to go off and retrieve LFS content not just for your local tracking branches, which ones you've previously checked out, but for every single ref, which is branches and tags that the server knows about. So that is a huge amount of data. I would only ever really recommend doing that if you're working in a very small team or in a very slow-moving repository. And in that case, that could potentially be useful depending on what your use cases are. So once you've fetched all of this content, you can use the git LFS prune command to go off and clean it up. So this is going to delete those objects from your local LFS objects cache. By default, it will never delete any large files that are related to the commit that you have currently checked out, and it will never delete any files that are considered recent, so a recent branch or recent commit. And it also adds this prune offset days to that sliding window from the fetch -- recent command. So by default, it will never delete anything that's been modified in the last 10 days, so 7 plus 3. And it will also never delete a commit or LFS files that are related to a commit that hasn't yet been pushed to the server. So it has kind of a safety mechanism there. But it also has this other safety mechanism, which I actually strongly recommend if you're working in a professional context, called prune verify remote always. What this means is that it'll actually go off and check with your LFS content store to see if that object exists on the server. So unless you're genuinely attempting to delete something locally that maybe you accidentally staged the wrong version of a large file and you're not really interested in tracking that permanently, I would recommend enabling this because it's just that nice additional safety check to make sure you're not deleting something irrecoverably. So that's how you can fetch more objects than potentially you might initially want through that smudge filter. But you can also configure Git LFS to fetch less objects and just leave some of those pointer files sitting around in your work tree. Why would you want to do this? Well, in some cases, you don't want all of those large binaries. Imagine if you're working on a computer game that had really heavy texture assets and audio files and model objects and all that kind of stuff, but then you were disciplined and you were writing good unit tests as part of that. Now, you don't necessarily need to assert anything against those graphics and things in a unit test, so you might configure your CI server to just fetch the text content for your repository and build that. And so you can use the LFS fetch exclude flag to exclude certain directories from being resolved using LFS. Or you might have the inverse of that You might be a specialist engineer who only wants to include a few select files from that repo. So for example, an audio engineer is probably only interested in sound files. So rather than pulling down gigabytes of other assets, they can just get the ones that are important for their team. And because these roles are probably unlikely to change like per checkout or per clone, you can actually configure it permanently using the fetch exclude and fetch include properties. And that pattern is basically just an ant glob. So and actually, it's exactly the same as the patterns that you use in your git ignore files for ignoring certain files from tracking in Git. So depending on how you use Git, you may want to avoid the sharp edges of using the command line in some situations. So instead, you can sometimes use IDEs and GUI tools, depending on their support for Git LFS. Fortunately, the JetBrains family of IDEs, does anyone use JetBrains, IntelliJ IDEA or AppCode? Yep, cool, a few people, awesome. So they appear to work with Git LFS out of the box, as long as Git LFS is on your path, which is nice. eGit, as of version 4.2, I was at EclipseCon earlier this year and sort of gave a similar version of this talk. And Matthias Son, who's the maintainer of eGit, said, yes, absolutely it works. However, you need to make sure Git LFS is on your path, which means depending on how you start up Eclipse, you'll have to have your environment configured correctly or start it from the command line with your path correctly configured. If you're using NetBeans, it also works straight out of the box. NetBeans actually shells out to Git for all of its Git integrations, so then Git just shells out to Git LFS as normal, so that's great. The bad news is the Xcode IDE doesn't seem to yet support Git LFS. Apple actually maintains their own fork of Git, which is based off an earlier version that doesn't yet have the extension points that were introduced to support Git LFS. So I forget exactly which that is. I think it's the pre-push hook it doesn't support. So that means that at the moment, if you want to use Xcode, you're kind of stuck with command line Git. Or you can use SourceTree, which, full disclosure, is an Atlassian product, but it's a free Git client GUI that you can use for interacting with your Git repositories. So it ships with Git LFS support, has like a little Git LFS drop-down menu where you can do stuff, although you don't typically need to use that unless you're doing something fancy, because you can just add, commit, push, and pull files as normal from the client, and it just works transparently. It also has a couple of nice features in that it will automatically repair Git LFS repos that look a bit hinky. So if that pre-push hook that gets initialized by the smudge filter isn't sitting in the hooks directory, it'll set that up for you. And it also reads through to your backend Git LFS cache, Git LFS store automatically, so you can get like binary previews and things. That's all I've got today so far on Git LFS. If you want to check out the documentation, it's sitting up at gitlfs.github.com. As I mentioned, it's a joint project between Atlassian and GitHub. It's supported in Bitbucket Server as of version 4.3. And if you like, you can follow me on Twitter. I'll tweet out the links to a PDF of these slides in the very near future. Other than that, thank you very much for your time.